Yes. So good morning, everyone, and welcome to today's session. Just you can wait for 1 or 2 minutes. So our speaker is about to start. So our today's speaker is Professor Yogesh Vijay Hote sir. He is working in IIT Roorkee. So once he will join, then we will start the session. Oh, okay. So good morning, sir.
Good morning. Good morning to everyone. Good morning.
Yeah. So, sir, shall we start, sir?
Yes, can start.
Okay, okay, sir. So, sir, before going to start, I would like to introduce our speaker. So, once again, good morning, everyone. Good morning, sir. So, today's our speaker is Dr. Yogesh Vijay Hote, sir. He is professor in the Department of Electrical Engineering, IIT Roorkee, with 25 years of teaching experience. His research expertise lies in control systems and their applications, mainly robust controller design, model order reduction techniques, mitigation of cyber attacks on power systems, and application in low frequency control and power converters. Over his career, he has authored more than 175 articles in peer-reviewed journal and reputed conferences and has mentored 12 research scholars to successful PhD degree in control theory and applications, with 7 additional doctoral candidates currently working under his supervision. He has also guided over 40 postgraduate students. Currently, he served as chairman of the Senate Committee for Scholarship and Prizes at IIT Roorkee. The single window office for scholarships and awards, coordinating key ceremonies and student support initiatives at Indian Institute of Technology, Roorkee. Dr. Hote is active in leading multiple sponsored research projects, serving as a principal investigator on grants from iHub, IIT Kanpur, CPRI Bangalore, SERB DST, and others, as well as contributing as a co-investigators of many sponsored projects at the Indian Institute of Technology, Roorkee. He developed NPTEL course Advanced Linear Continuous Control Systems application with MATLAB programming and Simulink, and authored the monograph Simple Approaches for Stability Analysis of Linear Uncertain Systems at the Indian Institute of Technology, Roorkee. He developed the flagship Control Theory and Applications Laboratory at IIT Roorkee, organized several short-term courses in control systems, and has been invited as a keynote speaker at numerous conferences and workshops. Additionally, Dr. Hote has been recognized among the top 2% of scientists worldwide in electrical and electronic engineering. Stanford's LGBR from 2021 to 2024. In 2021, he received prestigious IIT Roorkee Outstanding Teacher Award. And so now I would request our speaker, Professor Hote sir. So, sir, can you share your screen and start, sir?
Okay. Thank you, Dr. Arvind.
Welcome.
My screen visible to everyone?
Yes, sir. Yes, sir. Your
Okay.
IC voice is also audible, sir, and screen
Okay.
is visible.
Okay. Okay. So first of all, good morning to all participants. Also the organizing team which is busy here for this important workshop, which is related to adaptive control and power system. And most importantly, I'm also thankful to Dr. Arvind and his team for inviting me in this workshop. The topic of my today's presentation or lecture is fundamentals of robust control and its application. As this workshop is related to grid resilience and adaptive control evolution in a power system. So actually, the workshop is on adaptive control, but I am little explaining about the robust control. So the question arises in our mind. Adaptive means some sort. We can say we are adapting the things, and robust looks a best system. So sometimes our mind it will come that whether this robust control or adaptive control are the same thing. Any participant like to say something about it? Because your topic is adaptive control, this workshop topic, and I'm explaining something about the robust control. So adaptive and robust control are the same thing. Any participant would like to say? Dr. Arvind, am audible? Huh?
Yes, sir, you are audible,
Yeah.
sir.
So my point is like this: adaptive and robust are the same thing or a different. Any participant would like to say something?
Yes,
Yeah. Hello.
हाँ sir, actually ना they cannot.
Okay. Anyway. Okay. Okay.
Yeah.
Anyway, you can so that I can understand what the participant are understanding or not. Can you switch on the mic of one or two participants so that I can understand because it's online. Sometimes it's difficult
हाँ.
to see the participant and this one. Okay.
Yes, sir.
Yeah.
So they are writing, sir, in the chat box, not.
Okay. Okay. So
Yes.
anyway, it is difficult for me to see chart because that's
हाँ,
clean.
no problem, sir. You
Yeah.
can continue,
Anyway,
sir.
I will continue. I will continue. So the adaptive control and Satka
So,
robust control. Yeah.
hello.
Ah, yes.
Yeah, yeah. Robust means I think it's robust to the noise means if there's some disturbance happens, then it is
Mm.
actually it can sustain those noise. I mean, it is designed in such a way it can sustain those noises. And adaptive means I think means if some changes in the system itself happens, or I mean some condition in the system has been changed, then the control input will occur in such a way that it will adapt to the situation. It will adapt to the changes of your model. Mostly the model, I think it's adaptive is mostly related to the model, and the robustness is mostly related to the external noise.
Okay. Anyway, your answer is okay, but anyway, I would like to add some points. Adaptive control means it's clear from the word the control will adapt. So now the point is that as the situation changes, because when we design a controller, as you said, noise and everything, when we design a controller, we designing in such a manner that it will take care of noise and disturbance or other issues now. But sometimes the situation changes. Sometimes the situation changes. So now that situation, we have to change the controller also. Controller has to adapt. For example, let us say I'm talking about simple PID controller. Am I audible? Participant who is speaking with me. Hello?
Ah,
Yes,
yes, sir.
Yeah, yeah.
you are audible, sir.
Okay. Yeah. So now let us say PID controller. That PID controller we have to design for a system. Okay. So we have designed one PID controller which can take care of your noise also. And what happens suddenly, some noise or some disturbance comes. So same PID cannot be helpful. So now we have to design a controller such that the PID or the PID should change its parameters or now the controller will modify and we will get the desired results. That is particularly the case of the, we can say, the adaptive control. But what is called a robust control? Robust control is simply, we can say, whatever changes has happened. So your controller will be fixed controller. same controller will handle all these type of situations. Okay, so whenever, but now if you see the about it, just although there are so many points are there, I have given in a brief minor information about it. So the adaptive control will take care of the change of the controller will modify. And what I am saying that the robust control means some type of a controller which will take care of the worst case effect. The whatever happened in the worst case, that worst case can be handled by the robust controller. So now ultimate aim of all these control adaptive to get the desired result. So now which controller can be a better option? And here is the a power system application is coming. I hope my point is clear, participant. Hello?
Yeah, yeah, yeah.
Yeah,
Yes, it's
yeah, yeah. So now as an engineer, because we had to use it, I have given a simple point. Adaptive means your controller will modify. Here I am thinking robust, your controller is fixed, even though whatever changes has happened. So from a application point of view, which can be better? So now when you say here the controller is adaptive, means if you see the mathematical theory or concepts, the implement or the design can be simple. But when we talk about the robust control, because it has the same controller has to handle all the situations. So in that case, I feel that there can be issue of the mathematical complexities because same controls to be had. So then what can be a better option for the future? So I am feeling I'm thinking that better option for the future uh, from the application point of view is that we have to see the which type of application we are having. And sometimes, instead of going for a simple adaptive, simple, say, robust, we can go for the hybrid approach of adaptive and robust control. That can be a new research domain in power system application, although that is based on the type of application we can handle. So now we coming to the main because the topic is power and adaptive control. So maybe some of the participants are very new to this control, or maybe participants are purely from a power system background. For them, I would like to say something. What is the role of a control engineer, or you are let us say a control system expert? What has what work has to be taken care of? So the first important thing which to be taken care of is the modeling. Modeling, let us say power system is there. So power system is we have a power plant where there is a say turbine, generators, governors. So all these things are there. So now we have to model the all type of systems. Then we have to see its stability or we have to check its stability. And if the system is found to be stable, system is found to be stable, then we should know its performance. And its performance is not satisfactory or that is not up to the mark, then we have to design a controller. So the work of control engineer like this. Then sometimes the question has been asked, what is the control? Or control, is it a hardware or software? What is control? If you simply say control, is it hardware or software?
it can be both.
It can be
Both.
both. Okay. So if you talk about the system, okay, uh, system can be any power plant, a power converter, or we can say a robotics. Okay. If this system has some problem, some issues, then what is required? We have to drive that particular system. So there is need of an actuator. Am I correct? Am I correct? Actuator. Or
Yes.
I can simply give some other example. If the any person has a problem or health problem. If the health problem is there, that patient is supposed to go to doctor. And so we can say that this patient we call as a system, and the system is going to the doctor, and the doctor is prescribing the medicine, and then that patient, so doctor will write some medicine, and that patient has to go to the shop and purchase the medicine, and it has to take he has to take it, he or she has to take it. So in this complete process, our requirement is that our objectives to be solved. That is, let us say, blood pressure problem. Your blood pressure is up to that particular level, and after taking the medicine, it may observe that the, the patient may feel better. So in this particular complete process, where is the control? Have I understood? Have I understood? Participate my example. Hello, hello. Am I audible?
Yes, you are audible.
Yes, sir, you are audible.
Yeah, I have understood the problem now. We are understanding the what is control. Uh, that control, I have taken the example of a patient, then medicine, and a doctor. So can we say this complete is a control? Then where is the role of control? Now I can give some other. Now this is one example. Other example we can say the example of a power plant, an example of a low frequency control problem. And this low frequency control problem, suppose the load increases, and when the load increases, what happens? Sometimes the frequency drops. And let us say we have a steam power plant, thermal power plant. So in that case, the power generation is based on the flow, the steam. And the steam, there is a governor. In that governor, we can say certain wall is there. So let us say where wall is 50% open. Wall is 50% open. And accordingly, we have got the power. But suddenly load increases, this frequency drops. So now we have to increase the flow of steam. That means that the wall has to be open. So wall has to open, let us say 50% open. Now we have to open additionally, maybe 5% or 10%. So in this also, this is one power plant application, simple application. So where is the role of control is coming? I hope my point is clear to everyone. Hello?
To track the speed or to track the blood pressure.
Yeah. Now, so the actually, I would like to say my point is that the control is mainly a decision making. So the decision making here is that, particularly the case of an example of a doctor, doctor is not not doing actually any particular work in this process, because medicine is doing the process, patient is taking the, but which medicine to be taken? What is the level or quantity mg of that particular medicine, that is decided by the doctor. Because if you that if medicine we are taking for 10 mg, and doctor suppose by chance given higher value, then our patient has taken that higher value, then what happened? Instead of uh, uh, balancing the blood pressure, the blood pressure may reduce to very lower value. So in that case, that decision making plays very important role. So control is basically decision making, and that decision making, if it's not correct, then a problem comes. Similarly, in the example of a power plant, as the load increases, frequency reduces. Now, for that purpose, according to concept, wall has to open by 10%, but suddenly it is open more than 10%, maybe 20 or 30%. So what happened? The frequency, which is now earlier reduced, now it increases, so that higher value is not also create a problem to our system. So control, you can say decision making. Just like in official process, if some of the faculty members are here, Dr. Arvind, Dr. Arvind, am I audible? Hello, Dr. Arvind, are you here? Hello.
Yeah, you're audible.
Are you audible? So now, are you faculty or student? You are talking with. Hello.
Yeah,
What is your
I'm
name?
yeah,
Huh?
I'm in final year PhD almost in IIT
Okay,
Bombay.
very good, very good. So you can anyway in future you will become a faculty or some industry. When we follow some process in a government organization or somewhere, we go with a different process. Ultimately, approval is given by the director or the top manager of the team. So that final approval. So this control is just like a approval for something. Without this, we cannot go ahead. And if it is not correct, thing is not correct, ultimately we cannot reach to what we desired. And sometimes where application are very sensitive, if control is not designed properly, we will have some unusual results come across. So this is mainly about a control, the important role of the control. So according to my view, as we are the course is belongs to a power system where there is a requirement of controlling of the voltage, controlling of the frequency, so say economical balancing, and nowadays there are issue of the cyber security that is also related to your power plant. So other than the power plant, power system, there are this control helpful in all types of application. Let us say robotics, process control, electronics, everywhere. So according to my view, this control system or controller is the heart of all types of applications. Because if your decision is not correct, everything will fail. So therefore, as a control engineer, we have option to move to the different areas, or we can work in the different discipline also. So that's why the control plays a very important role. Then control theory research areas, classical control, adaptive control, optimal control, nonlinear control, and robust control. So there are different domains of controls are there. Ultimately, our objective design a control system for achieving desired objective with minimum time and energy. That is ultimate aim of all these techniques. Now we going with this robust control. So initially we try to understand why robust control is important. So now you can see a simple feedback control system. So H, we can say certain type of gain we can take. G is the plant, and K is the feedback controller, or like I say feedback gain also. So we can interchangeably take any values. Now simply I have taken H equal to 1 by S minus 1, G equal to S minus 1 plus S plus 2, K equal to 1. Definitely in our UG class, we'll see such type of example, and we are trying to obtain a performance, how to obtain the performance. We have to check the performance. Simply what to do now? We have to see this plant is working properly or not. What to do now? We have to determine output with respect to reference. Y of S by R of S. Is it correct? Hello? Hello, is it correct? We will try to obtain Y of S by R of S.
Yes.
Yes, okay. So now we have made some programming for the simple programming. So we have taken plant H, we have taken numerator, denominator, system transformation. Then plant G, you can see this plant G, H and G, and we have numerator 1 minus 1, denominator 1, 2. Then we obtain the transfer function 61. So SYS and SYS1. So this is basically G and H. So now they are in series. I think MATLAB's, I hope most of them are aware of this MATLAB programming. So here we have to determine ultimately y of s by r of s. That is, we need to close the transfer function. So in MATLAB, the G and H in series, so system to series SYS and SYS1. And then we obtained of closed loop transfer function. In MATLAB, there's a command feedback, sy3 feedback, sys2 comma 1. And we get a closed loop transfer function y of s by r of s. Now we determine this response, a time domain response and a frequency domain response. So you can see our response shows the stability. I think you can see the steady state, no transient, and we can reach to proper steady state. And we can see the frequency domain plot. We have got gain margin infinite, phase margin infinite, which is almost a very good stable system. No issue of the stability, and ultimately a very good system now. Is it correct? Is it okay for this problem? Hello? Is it fine? This performance?
Yes.
Yeah, performance is okay now. Okay. Now, as we are talking about initially, when I ask questions, we say some noise and disturbance. So now we try to understand simply a disturbance is added, U of S. You okay now? The disturbance. We added some disturbance. So disturbance can added anywhere. Now an input disturbance, some kind of output disturbance also. Some now let us say we have a D of S, input disturbance. And what we now there are two inputs now. One is R of S and other is input is D of S. Because disturbance is also an input now. Normally we obtain Y of R of S. So now an additional input has come. What to do now? So we have to obtain Y of S with respect to disturbance D of S. And now this is the transfer function we have got. So for this example, if you are taken, do we need to take ys by r d of s? Because normally we used to take ys by r of s. And after that, taking y by r of s, we are checking stability by denominator. Then we also um, determine the various responses, and ultimately we come to that conclusion. But do we need to have a y by r d of s? Particularly, I'm talking about the stability point of view. From a stability point of view, whether system is stable or unstable, do you need to take y of s by d of s? That is my question. Any participant would like to say? I hope my question is clear to everyone. Hello?
Yeah. So for stability purpose, only the eigen poles matter here. The
Poles,
yeah,
poles
but the
matter.
poles and the poles doesn't depend on your input. It depends on your system.
Okay.
The
So
closed loop system.
according to your view, we should not there no need to taking no need to take ys by d of s. Is it the conclusion?
No, for stability analysis, you only require the means. If it is a linear system, then the input doesn't matter for the linear system. It's a linear
Okay.
system. So the only the pole position matters. Eigenvalue position matters.
Okay. So ultimately, I can say I want to check whether this is stable or unstable. No need to determine the uh, response because ultimately poles and zeros, everything's are there. Ultimately, we are also seeing this response also. And the poles on the left hand side on the S plane will get the stable response. Right hand side, we get the unstable response. So ultimately, from what you speak right now, we can say that output with respect to disturbance DS, we must also get a stable response. Am I correct for this?
Yes. Yeah.
Okay. So
If it is
now, again, we did a simple MATLAB programming. Okay, so H and G. Okay, H we have taken, G we have taken, then system feedback. So all simple MATLAB. We are not use the simple programming concept we are use. 10 raised to 25.
So how?
Okay.
So,
Huh?
is it the same system?
Yes,
One.
yes, that's what I'm saying. Same thing, same plant. You can see, you can also try yourself. Okay, the same plant I have taken. You can see, I have taken HG, same plant, and this YOPS by ROPS I have taken, and that's why I have shown everything to you with all programming and all aspects I included, so that it is clear to everyone. And this is the response: gain margin, phase margin, infinite. Then I have taken Y of S by D of S, H and G like this, and the system is unstable, result is unsatisfactory. Okay, is it visible? My screen is visible to everyone? Hello,
Yes,
participant?
sir. Yes, sir. It is visible,
Visible,
sir.
na? My point is clear,
Visible,
na?
sir.
What I'm trying
Visible.
to explain? Yeah.
Yes, sir. Yes, sir. Please continue,
Yeah,
sir.
yeah.
Yes, sir.
Is it okay? No, I have shown a simple plan. I have not taken very complex things. Very simple thing I have taken. Okay, because ultimately, what I always feel that okay, after 25 years service, if you think everything from basic point of view, no, you can think about the more about the research. Okay, and fundamental plays an important role. That's why even I have taken the topic fundamentals. Okay, I will again come across these results afterwards. Now again, now we take another. I have taken H, same H, G and K. Now my H is 1 by S plus 1 and 10 S square plus AS plus 10 now. So now here I have taken A parameter. So I feel that or we decided that A is a very variable parameter. A is changing because now this is a linearized plant and everything is fixed. But in the actual plant, actually real-time plant, parameters are not fixed. They are continuously changing. Particularly, let us say we have inductance. This inductance has small resistance. Even a capacitor has small resistance. So that is also changing continuously. Even sometimes your say input voltage, particularly in power, that is also changing because let us say battery example of battery has some small resistance. So that battery resistance is also changing. So that means the thing is fixed. Everything is changing. So this means that the model is always changing. Am I correct? What I am saying? Or anything to be added here? Somebody would like to add some point, more point? Hello? Hello?
Yes, sir. Yes, sir.
Okay. What is your name? What is your name? Huh?
Sir, I'm Dr. Vishal, one of the organizers. Yes,
Okay,
sir.
very good, very good.
Yes,
Okay,
sir,
thank you.
sir.
Thank you for coordinating here. So, Dr. Vishal, am I correct what I'm saying? First problem
Yes,
is
sir.
okay.
Yes, sir.
The first problem is
Yes, sir.
okay.
Please
The
continue, sir.
second
Yes, sir.
and second problem I am thinking that the A is very okay. A changing. And this is the reality of the practical plant. Yeah. So here again I have done a simple programming for the same numerator N1, S1, then sorry, the G I have taken, and you can see N2, D2, I have taken A as a variable, and and I assume A as a one value first. You can see N1, S1, N2, D2, A10, then system series S1, S2, then a feedback and step S4. So now when we take an A equal to 1, we have got these particular results. Initially some oscillating behavior and then reach to steady state, but not satisfactory. But we assume that in practical plant E is also changing. So when I have taken A equal to 0.1, A equal to 0.1, so you can see again a highly oscillatory behavior. And this indicates that if you reduce the A to a very smaller value, performance deteriorates and sometimes system may be unstable. So the instability will come here. So just assume that here, assume that H is the one type of controller. Let us assume H is type of controller, and parameter is changing continuously. Parameter is changing continuously. So either this H should be adaptive one, adaptive type, or that H to be fixed so that whatever changes has happened in A, that controller will take care of this. I'm repeating the problem again. Now my problem is my system parameter is changing continuously, A changes. So either I can change my controller H regular basis, or I can have a H as a fixed controller. Irrespective of this, irrespective of this, you have a controller, we can get the desired result. Right now, we observe that just assume H is a one type of controller, we are not getting the desired results. So therefore, for this type of example, there is need to design a controller. I hope this point is also clear to everyone. Hello, what is your name? I forgotten, doctor. Yes, I do.
Sir,
Hello,
Dr. Vishal, sir. Sir, it is
Dr.
visible.
Vishal. Yeah,
I'm monitoring, sir.
yeah, Dr. Vishal. Yeah. So, Dr. Vishal, my problem is our point is clear. No? What I want to say that is we have
Yes, sir.
option.
Yes, sir.
Either we
Yes,
can
sir. Yes, sir.
change the controller or design a control so that all the changes can be taken care of. Okay. So now this is the one type
Right,
of
sir.
problem. Yeah. So performance is not satisfactory. Performance is not satisfactory when there is a parametric uncertainties. Now again, I have taken a problem. Now here I have done stability. That is stability means stability. One word we use. Now here I have added one word that is called internal stability of the system. Internal stable models. So for internal stable model, so here earlier I have taken this example. This y by d of s. This example I have taken. On a similar track, now we'll see the result from mathematical point of view. Okay, so here we have taken g as 1 minus s 1 by s minus 1, h is s minus 1 s plus 2. Then we have determined ys by r of s and ys by d of s. The same example we had taken earlier. Now we have solved it mathematically. And mathematically, what happened? Output with respect to r of s, we have 1 divided by s plus 3. And ys by d of s, we have got in the denominator, we have got s minus 1 s plus 3. So from equation 1, system is stable. From equation 2, system is unstable. That is, if you talk simply from a stability point of view, y by rs, system is stable. But if you systematic understand from internal point of view, that is ys with respect to d of s. Okay, you can say the system found to be unstable.
Anyhow, sir.
Yes.
So
Yeah.
if you have the D, then I think the system is inherently unstable, but the it is that instability thing is not observable if you consider the D. If you consider the R and if you consider the D, then it is actually observable. Its system is actually your system is actually unstable. I have seen that it has pole at -3 and 1, the closed loop pole.
Yeah. Okay. So
Yeah, minus
what?
3 and 1. Yeah.
Yeah. Okay. One minute. Yeah. So we take the same example. I think there is a S plus 3 is missing now here. Okay, S plus 3 is missing. Yeah, S plus 3 is missing here. Okay. So now we can take same this plant. If you take the same plant, okay, clear. So if you take YS by RS, you will take closed loop transfer function 1 by S plus 2. That's why system is stable. But when we take YS by DS, this term of S minus 1 will come. This term S minus 1. Similarly, for this example also, this example also here, this G is basically, here I have missed this point, S plus 3. So YS by RS, we get was S plus 3. But when we take YS by DS, we'll get in the denominator, we get S minus 1. So here, the important point of it, I would like to tell you here is that when we want to design some robust system, our system should be perfect in all aspects. We had to take not only YS by RS, you have to take output with respect to all types of inputs. It can be disturbance or we can a noise. And here's for specific example. I'm not saying that whatever I shown is true for every cases now. For the specific case, it is observed that output with respect to R of S is stable, but DS is unstable. I would like to ask one point. Why for this specific example, system is found to be unstable? Hello?
Yes, sir.
Dr. Arvind is speaking.
Yes, sir. Yes, sir.
Yeah. Yeah. So now your discussion is going on about the
Yes.
robust control. Okay.
Yes. Ji,
And
sir.
stability and one other point about internal stability. So my point is that uh, when we have to check the stability of the system, we have to take every input into account. Right now, for this specific example, uh, output with respect to references comes system found to be stable. Output with respect to disturbance D, system is found to be unstable. And the reason behind is that when there is a pole zero cancellation is involved in the plant,
Yes, sir.
Yes.
and when there's a pole zero, because here H and G, the one pole which is common to us, and this pole is basically unstable pole. You can see, okay, here S minus 1, S plus 2, and here S plus 3 will be there. But now this S minus 1 is cancelled in a mathematical way, but practically it never be cancelled. Practically, it will never be cancelled. Okay, so that was from a stability point of view cancelled. But when we go internally the pole cannot be cancelled, and because of that, it is reflected in the output as a unstable system.
Yes, sir.
Is it okay now? I
Yes, sir.
think,
Yes.
yeah, I think that one participant was earlier was speaking with me. That who is that participating? Other than Dr. Vishal, other participant was there. Who is the final year PhD? I think one participant is there. Final year PhD.
Yeah, yes, I got the pole. Because of the GH product, it is actually the pole zero cancellation is happening. The
Happened.
unstable cancel and
Yes. So now here, this is the point I have told from a mathematical point of view. Now we coming to the practical point of view, practical system point of view. Sometimes you observe that everything running fine, everything is right. Suddenly, at some moment, something has happened. Okay, and certain instability is coming. This indicates that normally our parameters are changing continuously. So the effect of pole zero cancellation it is very rarest phenomena because H is the parameter. H is the one that H has some numerator, G has some denominator, and although internally they are that there is stability is there, but because of the continuously change, exact point never comes. But in rarest of rare case, that point may come for small minor and say with the smallest of time or very less, very a microsecond, that particular point may come. And if your design is based on only wires by RFS, then unusual situation may happen, and sometimes we cannot understand why this has happened. Sometimes, we cannot get the reason behind it that why this happened. So there are some internal things which require to be tested for to make the system robust. So from the point of view that when we talk about the robust control, this indicates that we have to take output with respect to disturbance, with respect to reference noise, and even I'm saying that if your design is based on this week, whatever inputs are coming, so we have to take output with respect to that particular input. And now in this specific case here, system is unstable because of the uh, pole zero cancellation. So here I have the point I have written. Internal stability requires all signals within the feedback system remain bounded for all bounded input. Stability definition, when input is bounded, output is bounded. So here, when we talk about the higher level stability or robust control point of view, I'm saying that internal stability requires that all signal within the feedback system remain bounded for all bounded inputs. This is equivalent to the requirement of all possible transfer function between all input and output are stable. Feedback system is internally stable if and only if transfer function 1 plus kgh has no zeros in the right of plane and the product of kgh has no pole zero cancellation in the RHP, including the imaginary axis. So this is about the internal stability of the system. I hope this point is clear to everyone. So I have discussed about the robust control point. This is the point. Then another point I have explained about is this A point. AB is varying. Then whether to go for the change of control or some type of robust control. Now coming to another point now. Effect of the delay. Delay and is a very important challenge in nowadays because here everything is now automatic. So now there is transmission. Signal transmission is there. So now when signal from one point to another point, the signal is transferring. So there can be some issue of the delay. Even system has also some delay. System cannot start immediately. So that also produces some delay. So the robust control is that your system, our controller, should take care of that delay also. So here I'm going to explain one of this point with an example. So I have taken k 0.01 s plus 1 e raised to minus 0.1 s and delay of 0.1 second. And here I have done everything through MATLAB. You can say I have written a command G transfer function is k as 10. This k is 10 and 0.01 is input delay of 0.0. Okay, 0.01. Okay, 0.1 delay. So my screen is visible to everyone, all participant right now.
Yes, sir.
Yes, sir.
So,
So here I have taken a plant and a delay of 0.1 second. So now we are seeing the system is found to be a stable system. Delay of 0.1 second, a plant is simple first order plant. Delay of 0.1 second and plant is like this. And system is a stable system. Now, we are working on automation. Definitely it is a closed loop control system. So the closed loop transfer function is involved here. So this plant is in open loop. So here I am taking input delay 0.1. So now when I have taken a 10.01 input delay of same 0.1 second, and you can see that I have used the command feedback G comma 1 and system is found to be an unstable system now. It's going down now. You can see 10 raised to 31 now. Somehow very big, very high again coming down now. So this indicate very high instability. See, power of 10 raised to 31, and here a maximum magnitude of 10 indicate the stable. So here we have some observation about the open loop and closed loop problem. Input delay of 0.1 second. The system is found to be a very good stable system. Now, uh, this delay of 0.1 second in feedback system is found to be an unstable system. And this is happened for a simple uh, first order plant. And we are working on very complex plant. For first order, this is the observation of 0.1 second. And this 0.1 second is very small value. And even I have tried for 0.01 second also. Here, that result is not available to me, but anyway, I have tried here for 0.01 second also. In a closed loop, we have found a unstable system. Okay, this point is okay. I think that final year student, PhD student. Hello?
Yes, sir. Yeah.
Yeah,
Okay.
correct. What I'm saying here. I have added a delay of 0.1 second. System is stable. And when point delay of any system is closed loop, this I normally we say open loop, closed loop is better than open loop, but for this specific case, we observe that system is found to be an unstable system. And and here I have tried for 0.01 second also delay of 0.00. This small delay, still similar thing is happened. So because normally when we design a system from the theoretical point of view, YS by RS, we never bother about that there is a feedback signal is going from controller to actuator, actuator to plant, and plant to the again to the reference, the feedback. So many delays are coming on a regular basis. Although they can be very small, but delay is there. Am I correct? Hello?
Yes.
Am I correct?
Yeah.
What is your name? What is your name? What is your name?
My name is Mriganko Mukherjee.
Mukherjee, Reganka. Yeah.
Mriganko.
Midanko. Okay. I will say Mr. Mukherjee. Yeah. Okay now. Hello, Mr. Mukherjee. Yeah. So, have you understood this my point? Huh?
Yes, correct. Yeah.
But why this has happened? Simple example, simple thing. Because this can be a challenge now. Any participant would like to say something on this point? A plant, a simple plant, 0.1 second in open loop system is found to be stable, and we are working on automation. In automation, we have a closed loop plant, and in this closed loop, what I'm saying that there is a continuous transmission delay, maybe very microsecond like this. And here I am saying that for 0.0 second, same thing happened. So how to handle this type of problem or challenge? So this is also a problem of a robust control. So robust control involves the problem of this delay, the problem of the parametric uncertainties, and there's a problem of this pole zero cancellation effect. And also there's a problem of a non-minimum phase system. Non-minimum phase system is there exists a zero on the right hand side of the spin. And this happened because of the inertia of the system. So we need a controller which can handle this type of problems. Even if you take the example of uh, a hydro turbine, example of a hydro turbine, if you take see this plant transfer function, we have 0 on the right side of the S-plane. So that 0 on the right hand side S-plane means there is a called a non-minimum phase systems. And delay is also there. Just like if you take the example of same governor, turbine and generator, then here again we have to transfer the power from one end to another. You can say from a power plant to substations, then small substations. So you have the or power transmission is there, and we are trying to handle this through a closed loop control. Okay, so this delay is an important issue. So my point is that why it has happened, that system is stable in open loop. System is stable in open loop, but same system is unstable in the closed loop. But normally we say that in a language of a book, or it is written that closed loop is improve the dynamic performance of the system. It reduces the sensitivity of the parameter variations. Even will get a good steady state value. These are the important advantage of the closed loop or the open loop. Or in other words, simple word, automation is better than the without automation. So any participant have added some views or they have some remark on this?
Yes, sir. I think in the time delayed system, sir, due to non-minimum phase system, extra phase lagging are added in the system. Due to that, I think it is going to cross phase margin more than 180. So due to phase margin,
Yeah, yeah,
system will be unstable.
yeah. Dr. Arvind, yeah, this is also a correct point. Okay. But now we try to understand from a mathematical point of view. Mathematical point of view. Mathematically, how can we prove this point? Mathematically, we have to prove that why this system found to be unstable. That's the point. So the Dr. Mukherjee, Mrigank Mukherjee, hello.
So e to the power minus ts, you can actually divide by e to the power minus ts by 2 into e to the power minus ts by 2, and then do the approximation
Yeah,
1 minus ts by
yeah,
1
yeah.
plus
You are
ts.
correct. You okay? So then, what will happen if you do it? Yeah, either the way, no need to do calculations. So can be happened in that case? Or simply we'll not go with this one. Simply we can take e raised to minus point is 1 minus 0.1 s and simple approximation. Okay. E raised to minus ts equals to 1 minus ts. No?
Yeah,
Or e raised to minus alpha s equals to 1 minus alpha s. Okay.
yeah.
So what will happen actually from the mathematical point of view? Right now, I don't have that particular pen. Otherwise, I would have explained here. Or
It is having a pole at the right hand side. It is
which one?
having a pole at the right hand side.
Yes. So what happened when we go with the closed loop plant, and what happened in that case that time because that time delay when you open loop, it will not come in the denominator. But when we take the closed loop plant, that the numerator parameter is coming in the denominator. In open loop, there is no effect. But in a closed loop, whatever delay is there or non-minimum phase part is there, that will automatically come in the denominator in the negative form, negative values. And as per the rule of the poles and zeros, if any of the pole is lying on the right half of the split, the system is found to be an unstable system. I hope this point is clear to other participants. Other participant can also speak. Hello, Dr. Vishal.
Yes, sir.
Dr.
Yes, sir.
Vishal
I'm
and
here,
Dr.
sir.
Arvind. Point is
Yes,
clear,
sir.
no? Anything to be added? Because we are
No,
all
no, no.
teachers. So addition of knowledge is very, we have to increase knowledge, or even if you add some point, my knowledge will also improve. Okay, so it is.
Yes, sir. You are covering, sir, from basics only, na. So I think no need to add anything more.
Okay, it's clear. Huh? Point is clear.
Yes, sir.
Hmm? Yeah, yeah, yeah. So now here we can see all this effect of delays and then about pole zero cancellations and here about the performance with respect to DS and NS. So then additional point which has to be taken care effect of a non-linearities, environmental effect, and some sort of measurement issues. So if you have a system which can handle all these particular point, then we call as a robust system or robust control system. And in the control literature, uh, there are some techniques are available that is called H infinity technique, LMI techniques, which can help to handle this type of problems. And although we can observe that when we have a controller, let us say fixed controller, which can handle all these things, that is called worst case plant. Okay, so that means a lot of complexity may be involved when we go for the mathematical development for this one. However, I will appreciate the organizing team who have taken the topic of the adaptive control because instead of going for some fix, so adaptive can also be a very good choice. Sometimes controller can change it, okay, and uh, yeah, and it will be good option from the performance point of view because our aim is of everyone to get the satisfactory results. And here I think I want this one point in this particular delay point. What this particular point is happen for all type of system or not, or simply for some systems. So the answer behind is that because if your system is very fast, very highly sensitive, then we should be very careful when we go for the automation. Particularly your power system, very highly sensitive system. The response is very dynamic and very fast. So, effect of delay is an important challenge to be handled in the present situation. And if you take the other system, maybe the participant can may from other domain also, particularly process control domain, or sometimes of robotics. Sometimes system a little bit slow. In that case, this effect may not become. Or what I would like to say, even though delay is there, without controllers, system found to be stable, particularly the example of cases of process control. But in case of the power system may be unstable when that particular power plant is very fast in action. Now, coming to the next point, stability. Because now, when I'm saying that you take a power plant and the power plant, you do the modeling, and after the modeling, we go with the checking of the stability and see the performance. And definitely, mathematics plays very important role because although we're going for some MATLAB and simulation, everything, but ultimately the base of this is mathematical approach, mathematical development. So now I have come up with some point from the industrial application point of view. As I had told for earlier example, the stability depends upon the poles. Zero is there, so zero can modify the performance, but actually uh, the performance ultimately from the stability point of view, just like we can say absolute stability depends upon the denominator. But my point is that can it the correct one? But somebody can say it is correct because it is given in the book that in order to take the stability of the system, we have to determine the poles. And pole lying on the right hand side, system is found to be unstable. Zero is there, but nothing, no impact because zero can modify the performance. Then means as long as zero on the that zero position, there is no and pole on their own position on the left hand side, there is no impact on the stability of the system. Hello, Doctor this Mrigank, hello.
Yeah.
Sir, zero can introduce phase lag or lead that affects robustness margins.
Yeah, yeah. That is a part of the frequency domain. Yeah, just like we are taking the poles and zeros or the poles which are away from the imaginary axis. Okay, that also one margin, and gain margin and phase margin is also there. How much margin system is stable? Let us say we say your phase margin of 30 degree. That means we have a 30 degree additional margins is there. Okay, so that means we can add more and more gain that time. Okay, so more gain can be added. If your margin is let's say 10 degree, then we have a this option to increase the gain because ultimately this margin is connected to the performance, speed of performance. If the more the margin, more with the speed, we can have more speed of the response or more gain can be added. So this is also one parameter. But here my point is very fundamental point of view, and this is contradiction to whatever given in the book. Okay, this is my view. My view may be wrong. Here my view is that theoretically stability of any plant which is having numerator and denominator. Here I am not talking about the closed loop control or open loop control. Simply a plant, open loop plant or a closed loop plant, which is a numerator and denominator. For absolute stability of the system, we are checking the denominator, and the denominator has pole on the left hand side. System is stable, right hand side is stable. There is no impact on the zero from the absolute stability point of view. But here, what I would like to say here from practical point of view, zeros also have an impact on the absolute stability of the system. This is my view. Dr. Arvind and Dr. Prajap, Dr. Arvind.
Yes, sir. Yes, sir. Yeah, yeah.
I want
You
to,
are like we are
my
going.
point is clear. Yeah.
Sir. Yes, sir.
My point is like this because when we go for industrial application, because here your course is on some say power plant. So in power we are dealing with some models and everything. Clear. And stability is
Yeah,
one of the
yes, sir.
issues. Yeah. So from a practical point of view, I have this view, or particularly I'm thinking that way. Zero is also important from absolute stability point of view. So any participant have some other views or something to be added, they can add.
So practical system is nonlinear system. For nonlinear system, it's for linear system. The relative stability depends upon your that zero. If you have that means if you have zero, then the relative stability change. The phase margin, gain margin, those things actually change. But for the
Yeah.
nonlinear system, practical system are all nonlinear. That if you have more gain or more some pole in the right hand side means nonlinear system, you have to linearize the nonlinear system. So that this linear theory actually doesn't apply much. So,
Yeah. So your point is clear. Okay, what I'm saying, you have some zero on the right hand side, correct? Pole on the left hand side. Hmm? And this, I'm because you know that you say gain margin, phase margin, correct? So S minus 1 divided by S plus 2. We are determining the gain margin, phase margin, S minus 1 divided by S plus 2. Is it a gain margin, phase margin for S minus 1 or S minus 2 or something different system? You understood my point? Doctor, this Mukher, Merga,
Mukherjee.
Merga Mukherjee. Hello, Mr. Mukherjee.
yes, yes, understand.
My point is that when you determine the gain margin, phase margin for a plant, let us say, I'm going with this example, previous example. Just I will take one example. Let us say I have H equal to 1 divided by S minus 1, S plus 1. Okay, Mrigank?
Yeah.
Hello, Mukherjee. Yeah.
Yes,
Now
yes.
we determine the gain margin, phase margin, writing the command 1 divided by S plus 1. So is it a gain margin, phase margin for 1 divided by x plus 1?
No, it's for the closed loop system.
Yes.
For the
Now, yeah. This is for your closed loop. But here I am talking about a simple plant. Now, never talk about the open loop control or closed loop control. I am talking about simple plant. It can be open loop or closed loop. I am just taking the stability of this plant. Because this gain margin, phase margin, that is, you have a plant and there is a unity feedback. That is the assumption. Am I correct?
Yes,
Huh?
correct.
Yeah.
Yeah.
So my point is simple. We have a plant, and that particular plant, we are determining the denominator. Pole of the denominator. So the denominator on the left hand side, the system is found to be a stable system. But when I am seeing that with the same system, I am taking the practical domain. That system may be found unstable. That is my view. Practically. Although you can say that, sir, you are linearizing the system, and system is actually non-linear, and because of linearization, something may happen. Like that, you can say. Am I correct?
Yes, correct.
Yeah,
Yes,
you
yes.
are saying. But I am telling you that from the linear point of view, also we can understand this phenomena. Means instead of thinking most of non-linear, from linear point of view, also we can understand the phenomena why when this happened. That is my point.
Yes, correct. Yeah, you actually pole zero cancellation. If you consider the noise that way, then the some pole zero cancellation was happening because of that GH product. That time we have also seen that is the unstable thing is unobserved.
Yeah. So the pole zero cancellation here there is no even pole zero cancellation.
Yeah.
Pole zero cancellation is specific effect.
Mm-hmm.
Pole zero cancellation is the one type of specific effect. Here I am not talking about specific effect in generalized manner. We are thinking in a generalized manner. We are thinking.
Yeah, if you have some noisy signal, then
No. You are correct. No, there is no noise, no disturbance, nothing. No noise, no disturbance, no time delay, no parameter variations. Correct. Nothing is there. No, it is simply a very basic fundamental things, which is contradicted to what is the language of the book.
yeah,
Because
then
here my give my statement, although it is my view, I cannot say it is a generalized statement. Okay, it's some simple my practical view. In order to check the stability of the system, for absolute stability, zeros also plays important role. Zeros have also an impact on this. Means if you take thinking the system from linearized point of view, the linear system may be stable, but same system we go into practical aspect, system may be unstable in respective of your noise and disturbance. Okay, my statement is clear to everyone. My statement is clear.
Yes.
Okay, so now I will try to explain this point this way. Uh, is it clear? Simple plan. G of s equal to k tau s plus 1. This is plan. Is it clear? K is the gain, tau is the time constant. Okay. So now what I have done, I have taken this k in terms of k1 and k2. Because this gain is, we are increasing the gain continuously. Say k1 and k2. So now k2, k1, 1 plus tau s. So now we assume that this k2 is just like a some sort of proportional controller to the plant. Our original plant is same, k tau s plus 1. And here I have taken k2, k1 tau s plus 1. And this is a proportional controller. And this k2 can increase from minimum to higher value. But one thing is very clear to us. Whatever k2 is there, this plant is always stable, either in open loop or in closed loop, because the stability depends upon the denominator. It is a simple first order transfer function. 1 plus tau s equal to 0. So S equal to minus 1 by tau, S equal to minus 1 by 2. So irrespective of the K1 and K2, system is always stable. This is my view on just looking after this simple example. Hello, Dr. Arvind. Huh? Hello, Dr. Arvind, are you here? Hello.
Yes, sir. I am listening, sir, and watching.
Have you understood my point? Is it okay? My point, what I'm saying,
Yes,
irrespective of our K1 and K2, okay, why
yes.
whatever K1 and K2 system is always stable. The open loop or closed loop, whatever you can take. This is the viewpoint just looking after this, irrespective of the time delay, irrespective of noise, irrespective of disturbance, anything. Just a simple system. This is the conclusion. Just looking after it. Okay. Hello, Mr. Mrigank. Yeah. Mukherjee.
Yes, sir.
Is it okay? Right now, my point is clear. Simple point. Okay. Just whatever the language of the book I am explaining, irrespective of K1 and K2, system is always
Stable.
stable. Okay. So now I will move further. So I returned. As long as K is a part of the actual system, then we can say that first order system is stable. But now here I am seeing my view. Okay. Theoretically, root locus, thickness plot, time response, and definition is correct, but practically it may not be correct. Practically, may not be. And again, is my view. Sometimes sometimes for system to system view can be incorrect. But anyway, this is my understanding, practical understanding. So now I'm explaining why I'm saying like this. Now what we have done to understand this point, we have taken H and G, and we have taken a closed loop plant here. So same K tau s plus 1. So K tau s plus 1. Same way I have taken this K as K involve K1 and K2. And this K2 is, let us say, variable, just like a proportional controller, just like a droop control, which were in power plant. So here we have a negative feedback. So here same thing I have written here. K2 is basically a proportional controller. K2 is basically proportional controller. So when I started my lecture, I told about the basically what is a control system. The control system involved a controller, control input, actuator, system, and feedback. So now what has actually happened here practically, this K2 is a proportional controller, and this proportional controller where that signal is moving is to the actuator now. But in real time we cannot see actuator, but practically actuator is there, and this actuator will drive the system. Hello, Dr. Vishal. Am I correct, or do you want to add something over here?
Yes, sir. Yeah, you are correct, sir.
Dr. In the real time plant, what is the observation? My observation is that we have some controller giving signal to the control signal to the actuator, and actuator drives the plant. Correct. Okay. So now here internally some actuator is there, and K tau s plus 1 and Y is by RS. So now here I am saying this K control input, control signal is given to the actuator will drive the system. And now here, is it visible properly, this screen, this result?
Sir.
1 by s plus
Yes,
1,
sir.
and my k is 100 now. K is 100, correct? So now to reach the steady state of 1, we have got exactly very good response. No problem as such. You can see that there is your rise time very minimum, time cost of very nothing we can say negligible, and reach to very good response. But because now as a control engineer, we not only handle the stability numerator denominator, we are not only handling this noise and disturbance, we checking the performance. Always the control engineer see what type of control input is coming. So the control input has to drive the plant, and practically it is not possible that all the control input will be drive, all the control input will be driven by the actuator or all is whatever control input coming, it never possible that it will drive completely the actuator. So here we can see the control input coming from here. Practically, the control input coming from here is say 100. And you can see if you provide such type of control input to the your actuator, the one thing is that control actuator will not work or it can damage to your actuator. This is my observation on this. Therefore, what my point is that because theoretically, okay, stability depends upon the you can say pole and zeros, but practically the control input always plays important role. Here it is not even I can show here show the closed loop. Even open loop also. Open loop control is there. Open loop also involve controller or plant. That control input is there. That control input may damage to your actuator. So, Mr. Mukherjee, Mukherjee, hello.
Yeah, correct, sir. I understand what you are.
You understood my point, huh?
Yeah, yeah. Depend
Just
upon,
like
yeah,
that.
yeah.
You are
Also see
from
the
which
concept
place?
what. In
Mukherjee, you are
robust.
from which place? You are from which place, Mukherjee? Huh? You are
So
from
I
which
am now
place?
in Mumbai. Now in Mumbai, I am from Bengal
Good.
basically.
Okay, no problem. So you are from Mumbai. So now, so one day I may come to Mumbai now. Okay, maybe next month. Clear? Huh? So assume that will you invite for me some lunch or dinner? Will you invite me? Huh?
Yeah.
Okay?
Yes,
Huh? Okay.
electrical.
Yeah, you will invite me definitely. Yeah, I will that. Okay. Then we will go to a good hotel, Taj Mahal Hotel. Okay. Okay, I will sponsor this. Okay, Taj Mahal. We will go there. Clear? Huh? Uh, we'll go there, and then definitely we assume that I am a linear plant, or just like you assume me a transfer function. Clear? And then what we can do, we will try to eat chapatis. Okay, chapatis and something. Okay, and then let us say initially you're going for me for 4 chapatis, correct? Or that fulka we can say in that language. Okay, so 4 I have taken. I have a stable plant. You are giving me 4. Then you are going to increase me 6. What will happen? Hello,
Yeah,
Mukherjee? Huh? You
yeah,
now
you may.
you initially you saw me 4. You have told me accept sir take 4. Then you said sir you can add more additional 2, that is 6. So even though I am perfect, I am stable. What you are doing, you are adding up something. Okay. And lastly, you can say to me, you can say take 10. Okay. So you can see everything is stable. You are adding more and more to me. Clear? But at one particular point, okay, I will say no to you. Okay. So now, even though I am thinking of from my point of view, but practically this can be happened. So similar thing, just I have given an example. Similar thing happen. Clear? So even though we have a plan from theoretical point of view, you can get every stability. But when think about the practical point of view, that practically some actuator is required, and so system may be some instability may be happen. So therefore, my point is that Suppose we are doing analysis from the transfer function point of view. Okay, so there can be some problem of the stability, even though from theoretical point of view, system is found to be stable. So you have to always monitor what type of control input is coming to us. Sometimes, in our research articles, we can got good publication, we response. Okay, but what type of the control input is there? That is also important. So sometimes even in review also, when we publish some papers, the reviewers may always ask, what is your control input? That control input to be checked. It should be under certain limit so that in practical way, in a practical control system, we get the desired result. So, Dr. Arvind, is it okay? Or do you want to add more point here?
No, sir, I think you are correct, sir. Like in practical systems, if we will
Uh,
go, we will give more inputs, means the
uh,
limit more than the rate limit, then that
uh,
system definitely will become like unstable like that, sir.
Unstable, but theoretically will be stable because in a mathematical point
Ah,
of view. Yeah.
yes, sir, yes.
Okay. So that is the view. So that so all the participants who are coming here, who are like to work in control domain, or anyway, control is important for every system. So always you check the what type of control input is coming before going for the real time application. So ultimately, my conclusion is that my view is that stability of the system depend upon the pole denominator, but practically stability depend upon the poles and zeros. That is the gain of the system. Now we coming to the ultimately I want a definition of the robust control. What do you mean by robust control? So the ultimate goal of a control system designer is to build a system that will work in a real environment. The particular property of a control system must possess to operate properly in a realistic situation is called robustness. So you can see this book, the definition is given. So now an example here, a controller must perform satisfactorily not just for one plant, but family of plant, just like G of is equal to 1 minus S minus B. So B equal to 1, controller can be designed for our system. So the practically the system should be stable not only for one particular value of this B, but for all the values lies between 0.1 to 1.4. And in addition to this, the system is to satisfy the performance specification, such as steady state tracking, disturbance rejection for all values of A in a specified region, so that we have some for this a robust performance. That means system should be not only stable for one particular values, but all values for and that for all values, it has to take care of the steady state tracking, all disturbance rejection, even noise is there, that to be taken care of. Then, then we can say that system is robustly controlled or robust control. That is, it involves robust stability and robust performance. So now because of the some time, because 2 hours time is there, so I'm skipping some slides about the, and I already explained that we have to determine y with respect to rs, ns. So the mathematical part is there. I'm skipping this some part here and coming to some important theorem of the robust control theorem. One important theorem on the Characteristic theorem, which is very important from the robust control point of view. What is this Characteristic theorem? It says that whole family of an interval polynomial with real coefficient is Harvit's if and only if four specific chosen well-defined polynomials are Harvit. Thus, by merely testing the stability of four polynomials, we can ensure the stability of the class of four polynomials. Here I am saying that your plant has some uncertainties or parameters are varying. So when the parameters are varying, if you see simply from the trial error point of view, we have to check the say more than 1,000 plants or more than that also. Even that case also we don't know whether system is stable or unstable, because if the even small value is missing, system is found to be unstable. So this is the Catton's theorem is very a good theorem or a benchmark theorem from the control point of view or application point of view. This says that in order to check the stability of the system, we need only four polynomials, and that four polynomials are called the Khartono polynomials. And this is important theorem for particularly when we call the system is interval, when parameters are varying. So here, this is the plant K of S equal to 1 plus G of S, A0, A1S, A2S, ANS2N. This is the characteristic equation we can say, or we can say transfer function Ys by Ns. So we have numerator and denominator, and the denominator we have this plant, and parameters are varying, and there are minimum, and you can see this for all this plant A0, A1, A2, A0, A1, A2, X0, Y0. So X indicate minimum value and Y indicate maximum value. X indicate minimum, Y indicate maximum values. So theoretically, we see that what we can do in order to check the stability of the system, we can vary A0 from X0 0.1, then we keep X1 or X2 Xn fixed. The secondly, I can change X0 to X0 to 0.2, then again other fix. So this type of arrangement, we have to do it for all polynomials, and that's why I told earlier that we need some infinite number of polynomials, and even and then you're checking this all polynomials. It is a very toughest task. Although we can say somebody can say we have some software MATLAB, but now we are going to see the fast process. The fast process, even a microsecond is also important. Okay, so our aim is to reduce the simulation time also to checking the stability of such a plant with some trial and error procedure. It is a very tough task. So therefore, to solve this problem, what theorem is coming? Khartono's theorem. He said that the stability of this particular polynomial, we require only four polynomials. Hello, Mr. Mukherjee.
Yes, sir.
Is it okay? What I have understood my point?
Yeah, got
In
it.
order to check the stability of this type of plant, uh, we need some more say equations to be solved. I can say simply equation right now. Okay, so and then it is a tough task. So this problem has been solved by Khartono's theorem. And now about some historical things about this Khartono's theorem. This Khartono theorem was developed by Khartono in 1978. But what happened to this theorem? From 1978 to 1984, this paper was in only in literature. Nobody has taken the look on this particular theorem. So what may be the reason behind is that because the Khartono is basically a mathematician, a mathematical control theory. Without knowing the importance in the robust control, he published the paper, and because of the more complexity of this theorem, nobody has understood the importance of this theorem. Hello, Mukherjee. Have you understood my point? What I'm saying here? From 1978, hello?
Sir.
Hello, Dr. Arvind. This
Yes, sir.
point.
Yes, sir.
From normally we see publish the paper. Okay. What we
Yeah, yeah.
want is
What
people
are
should
the
read.
polynomials, sir?
Yeah.
What are the four polynomials? All the max min
Okay.
combination.
I will explain. I will explain after. Yeah, I will explain this point. First of all, we see the historical things. What I said, 78 to 84, nobody has understood this. So naturally, what we feel that our work should be read by the researchers, and then when people understood our concept, and then people can work or researchers can work on this term. That is the reality of the research articles. And the Dr. Orville, is it okay? My point. What our research is not for our himself. It is for the society. Okay, whether people can understand, they can do in application. But particularly for this theorem, because of the little complexity of this theorem, even the theorem is neat, uh, but to the best of my knowledge, that time researchers have not understood And what happened in 1984, NT said that this B.R. Banmesh, the researchers, he came across this theorem, or he has understood this theorem, and this paper indicates a simple proof of this theorem. Only proof, nothing more on this. And again, all this paper, B.R. Banmesh 84, 87, case Jung versus Wong 1987, R.J. Minchali and the scientist 1989, and lastly S.P. Bhattacharya. This S.P. Bhattacharya is basically a BTech from IIT Bombay and work in Texas. And I think last 6 months before he was expired, and he was the key person in the robust control. He had done extremely great work in the area of interval system and robust control. And lastly, the most what my point of view, what I feel, I observed that the most simple proof of this Catton's theorem is given by S.P. Bhattacharya in 1989. So now all this paper is only to proof of this theorem. Now, Dr. Arvind, uh, is it okay? My point
Yeah, it is very good, sir.
clear, na? So now
Yeah.
the proof of this theorem is given, and now the when the things are come out, and we find that the application is so simple, and definitely uh, we should give the credit for this to Caratono. Such a simple, such a concept he come across, and uh, following and given the solution of all practical problems. And because of the theorem, many of the PhD scholars have done a PhD only on Caratono's theorems. Really a great work by this Caratono. And you can see that simply if you do mathematical point of view, so many polynomials required, but he said a simple four polynomials. So now how to get the polynomials? You can see that these are the x0, x1, x2, y2, minimum values and maximum values. And a minute. Uh, Now here, so how to write a polynomial? He said his arrangement. In order to format the polynomial, he said you take two minimum values x0, x1, then two maximum. So x0, x1, y2, y3, and then again x3, x4, then y5, y6 like this. There is two minimum and two maximum. Then another polynomial k2, first minimum x0 minimum, then take two maximum y2, y3, then two minimum, two maximum like this. So I'm again repeating this procedure. For first polynomial, you take two minimum, two maximum, two minimum, two maximum. Second polynomial, take first minimum, then two maximum, two minimum, two maximum. And the third polynomial, we take first maximum, then two minimum, just like x1, x2 minimum, then two maximum, just like y3, y4. And last polynomial, two maximum, y0, y1. You can see x indicate minimum, y indicate maximum. So two minimum and two maximum values to be taken. And you can see the condition minimum, minimum, maximum, maximum, minimum, minimum, maximum. Here minimum, sorry, this K1, you can see K1, two minimum, two maximum, two minimum. Second, minimum, two maximum, two minimum. K3, maximum, two minimum, two maximum. And K4, maximum, maximum, minimum, minimum, maximum. So this is the arrangement has been explained or given by the Ketano, and he said that only four polynomials are required for checking the stability of the system, and that gives necessary and sufficient condition for stability of the system. Particularly if you talk about the Lyapunov criteria, which you might have studied, that only gives the sufficient condition, but this Ketano gives the necessary and sufficient condition for the stability of the system. And we can see through simple numerical example, you can see G of S equal to K, S plus A, S plus B, and you can have a parametric range varying from K has some range 200 to plus minus 20, A equal to 4 plus minus 0.5, and B equal to 6 plus minus 0.1. So these are the variation in the parameters. And then we have determined the closed loop cache equations. And this is a uncertain polynomial. And then we are converting this into a integral polynomial. Let's see, this is integral polynomial A3, A2, AB, A0. And here we have a independent uncertain polynomials. And so this is 180 is the minimum, 220 is maximum, 70.5 is minimum, 31 point maximum, 8.5 minimum, 11.5 maximum. So this is basically an independent uncertain polynomial. And to this independent uncertain polynomial, just like the procedure I have told you earlier, we have to determine the four polynomials, and these are the four polynomials which is determined by a theorem that is called Khatonos theorem. We require four polynomials. So here minimum, two maximum, minimum to maximum, and here maximum to minimum, and maximum minimum. It's the same arrangement which I told here earlier. This arrangement has been used, and you find that particularly this example or for this example, the first two polynomials are stable, third one is unstable, whereas fourth is stable, and ultimately system is an unstable system. And in this way, we can check the stability of the systems. And this is very much important theorem. And the problem of the robust control, particularly internal type of robust control, can be solved using this particular theorem. Although there is another technique which is called H infinity technique, but you can see that the complexity on this one that can be more. Moreover, what advantage of this phenomenon is that you can design a robust control for interval type of system using a simple PID controller. Whereas if you go with some complex uh, methodology, HFT control, the challenges which involved here, in that case, the order of the plant will be the order of the controller. For example, if your power plant is a 1000 order, in a HFT design, the order of the control is also 1000. But as you know, from an industrial point of view, the order of the controller, or we are normally going for the PID type of controller in the industrial domain. And the industrial domain, if you tackle the problem of the industrial by PID or robust PID, that can be solved by means of this Khatonos theorem. So you can see that a lot of research paper are available on this theorem. All the within this limited time, it is not possible for me go with all methodology and everything. My aim is that to you to tell that what are the fundamentals which are required, particularly in the domain of robust control, and what are the simple theorem, because ultimately our aim is to go for the simplicity. So I feel that this is a very simple theorem which can be helpful to the industrial point of view. Although there are some other theorems are there, just like a small gain theorem here there, which can be also helpful in the following uh, uh, the problem of the robust control. So here because of the limitation of time, I'm going to directly small gain theorem, say GS and HS. So we can say G is a plant and HS is some type of uncertainty. And if you use this Nyquist plot, magnitude of GS and HS less than 1. So this type of concept can be helpful in handling the problem of some uncertainty, that is small game theorem. So what I'm concept involved, you take G, see the disturbance here, and in case of Nyquist plot, we have unity feedback. Here we have H in the feedback. It is one type of uncertainty. So G and H, magnitude of G of or norm of this must be less than 1. Okay, if it is there, the system is found to be a stable system. Okay. So this is all about the robust control, stability issues, and fundamentals involved. So again, today the important issue of the cyber security norm. Particularly, your topic is on the power plant. Now, so many techniques and so many approaches are available to you. The challenge is of the cyber security because your control is stable, everything has been done, but some additional impact has come which is not known to us. Then how to handle this one? So my observation is that our control theory can also be helpful. Nowadays, there is a era of AI, artificial intelligence, and there's so many concept and so many things are available through AI for cybersecurity application. But my person feel that still there is a important role of control in the cybersecurity issue. Cybersecurity means detection can be done easily, but for mitigation purpose, your control theory will be helpful, or robust control technique can be helpful. So this is all about these things. So thank you, Dr. Ravind, Dr. Vishal, for inviting me this important workshop and on this power system with the adaptive control. Here I have explained about the robust control, and thank you for taking such a lead, which is helpful for the student participants and everyone. And mostly, and again, right now, I am thankful to this Mr. Mukherjee who has communicated with me, and all the best to you, and also all the best for the participants who have joined for this my session. And still, if you have any doubt, anything, you can communicate to me through my email. Although because it's limited time, it is not possible to explain each and every point. But if you drop an email, anything about control problems, I may help you. Thank you once again.
Yeah, thank you so much, sir, for giving your valuable time in despite from your busy schedule. Really, sir, your lecture will be beneficial for us, and you had given your lectures from basics of the fundamentals. So really, it will be helpful who are also not from the control background. Maybe some participants maybe from power system background, but for
Yeah.
them also be really helpful, sir. So if audience, if anyone is having any doubts or questions, you may ask from the sir if anyone is having doubts. Yes, so yeah, you can unmute and you can ask if you are having doubts. So, thank you, sir. I think no one is having doubts. You already
Okay.
covered
Yeah,
the basics only.
So
So, and you
one thing,
also asked in between that. Yeah, okay, yeah, ask.
yeah. Okay, Raj.
so one thing that this robust problem is basically optimization problem. Am I correct?
Yeah, because the robust involves, we can say the robust optimal is a part of robust control. We can say optimization.
Okay, actually, means in robust control formulation, what I have seen that they try to minimize the that control effort,
Yeah,
the norm of the U, the control
yeah,
input,
yeah.
the
Correct,
condition
correct,
that
correct.
you have to be in the stable domain. Means the constant
Yes.
and stable. That is the LMI problem formulation that I
Yeah, yeah,
understand.
yeah. Or I can simply add to you. Let us say a plant is there. There are parametric uncertainties are there. Okay. So let us say there are some multiple. Let us say there are say 10, 100, 1,000 plants are there. So the robust control means that that in that particular which is the worst case plant. For the worst case plant, we have a controller. We can give the result. If the result is true for worst case, then it is true for all cases. That is the simple theme of the LMI, or which we were talking about the HPT control. That is the- Yeah.
Okay, so then that H infinity controller, this kind of control formulation is not real time. No? You have to tune it in offline method. Then you can actually implement it.
No, no. See, actually, from industrial point of view also, okay, that can be implemented. But what I'm saying now, implementation is a real challenge. That's why you can see in industrial domain also, more than 80% controllers are of PI type. Even I have taken a training where I have seen that the still controller is of belongs to PI type. So when going for some controller, for example, you talk about HTTP controller, I think order of the controller is 1000.
Okay.
Hello. So now you can see the execution time process time for this. Because when we from one point to another point we are moving now, there is transmission is there, some delay may involved. So when we design the system, we have to take all point into account. So, for example, you said we have done the optimization problem challenge. Okay, so control is perfect in simulation point. Correct. So now when you're going for a real-time implementation, in a execution process from control input to actuator, suppose more time has been taken. So when more time has been taken, from classical point of view, zeros have been zero on the right hand side has been generated. Am I correct? You understood my point? Hello?
Yeah. Yeah.
What
Yeah.
I'm
Yes.
saying, your controller and control signal actuator, this is the position, and you are design an optimal controller. But in that process, that execution time, the delay comes. When the delay is coming to here, practically the more zeros have been generated on the right hand side. And when the coming to the automation point of view, that zero will affect the stability of the system. Therefore, when we do design the practical system, we have to take all aspects into account. Therefore, my point is that when we're going for a simulation point of view and practical point of view, we have to balance the both the things. Means something you cannot design a system which is having the 0.001 time constant or very minor smallest rise time, because theoretically is correct, but when you go for practical, we require the actuator of that capacity now, that capability. When you go for the high actuator, means your cost is also involved. Hello, Dr. Mukherjee?
Yes. Yeah. Yeah. Yeah.
Are you correct?
Yeah.
Okay, so theoretically you can design any controller, but you have to see the its real time aspect. So here the control input, what I was saying earlier, that also to be checked before going for the actual implementations.
Okay.
Thank you. Thank you.
So if anyone is still having any doubts, you may ask. Otherwise, we can close the session. So thank you, sir. I think no one is having doubts. So now you can leave, sir,
Yeah, if
meeting,
you have
and we
still
are
any
closing
doubt
the
or any
sessions.
confusion,
So
anything,
thank you
okay?
once again, sir, for
Yeah.
giving your valuable time, sir.
Yeah. Again,
So,
one thing I would like to tell that one thing.
mm,
Suppose any
I
theory is
think
there, when something statement is
I'm
there, it may possible that for some cases it may not be applicable. Just like a example of a route criteria, when we talk about the first column of the route array, in many of the lectures I used to tell that it is not that in first column system is always stable. There are some cases that even though the first column system is stable, but actually practical way or in response system is unstable. Yeah. Okay, Dr. Arvind, thank you.
oh, okay, sir. So now I'm closing the session, sir. So thank you, sir. Thank you once again, sir.
Thank you.
Okay, sir. Thank you.
Okay, I'm leaving.